Welcome to the session. In previous session, we have seen about the design of a mechatronic system and the element of mechatronic system and the applications and scope of the various mechatronic systems we have seen. In continuous with that, in this session we are going to see about the various types of sensors, the definition of sensors and the definition of transducers. You see here, we as a human being, we have the various sensors inbuilt to us. The eyes, ears, nose, everything belongs to a sensing element. That's what I have told here. The human being collected information from the surroundings using their own sensors, like the eyes, ears, nose, skins, etc. in order to perform a various tasks. The sensors used to take a measurement of a physical variable. What it is, we are measuring some temperatures, we are measuring some speeds using pressure generators and thermocouples. Right? Various measurements we are doing. Right? These measurements are to be converted into the electrical quantity. It means signal conditioning to be done. So those things are divided into the category of sensors and transducers. We will see about one by one in the upcoming slides. You see, a device which provides a usable output in response to the specific measures. So we are converting a physical element into the electrical usable form, which can be easily measured. The room temperature, which is to be measured first. The speed of the motor to be measured first. There we need to use the sensor. Right? You see, a device which provides a usable output in response to the specific measure. What we are measuring as a temperature to be converted into useful form. There we need this element, the sensors we need. Right? A physical parameters into a signal, which means a readable electrical signals which can be converted and can be controlled. That can be measured electrically. Right? A transformer, example, I'm giving a transformer at input of temperature, what I told you, input of temperature into a change in the resistance. Right? A simple sketch we can understand here easily that a quantity being measured. Here we are measuring. Quantity being measured, it is sensed element. And it is this response of signal is given here. The response of signal is given here. See, a sensor is an element which converts input into the useful form of an electrical quantity. One form into another form, a temperature into the resistance. Right? So such conversions we need for the measurement. Therefore, we are using these sensors. You see, I have given few examples for this transducers. It's nothing but a sensor. We are told it is a sensor, but it is to be transferred from the sensing to the one form of energy to the another form. We have to convert. That is done by the transducer. The name says transducing. Okay? The term transducer is often used in place of sensors. Whenever we are using the term sensor, then obviously the word transducer should come there, because the sensor cannot be used. It should be transferred to the another form, from the temperature to the electrical form. Right? Therefore, the transducers are defined as element that converts a signal, temperature signal, speed signals, of one form of energy to the another form. I have given some examples here. It may be a non-electrical quantity to the electrical quantity. It does not mean it should be the electrical quantity. We are just defining it as a one form of energy to the another form. Right? What may be the another form? See, sound to the electrical quantity. We are using the microphones day to day. We are using the microphones. Right? So this sound energy, what we are talking there, is converted into the electrical form through the mobile phones. So it contains a transducer, but it senses the sound. Then a sensor is named as a transducer. Thus, all the sensors are transducers. So I am telling all the sensors are transducers. So electrical, one more example, the electrical to light energy. Where it happens, we are supplying a electrical energy in the lights, bulbs, it operates. So the light bulbs are belong to the one type of sensors and transducers. You see one more, the electrical quantity into the mechanical quantity. Where it is the motor, we are supplying the electrical, supply to the motor, it rotates, converted into the mechanical energy form. Therefore, we can tell this one form of energy to the another form is done by the transducing element. One it is a sensing element and one more is a transducing element. What we are told, I have converted in picture format here. You see, the quantity is being measured. First, we have a sensing element here. Right? It is sensing. It's a signal. The response signal is given here. Response signal. And this signal conditioning to be done, it is to be transferred into the electrical format, to the electrical, to the light, to the mechanical. Somehow, some format to be changed. That is a transducing element. It is not an electrical element. It is a transducing. Somehow it changes from one form of energy to the another form. From here to here, it changes out. So it finally we will get the output of from one energy to another. Therefore, I am telling this all the sensors are named as a transducers. Thus, the sensors we are naming as a transducers. Whatever available is to be sensed and it should be converted to another form for the useful form. Then only we can able to use. Right? Therefore, the sensors are transducers. Right? Few more examples I am giving here for this sensors and transducers. You see, I am using a temperature sensor here, where the temperature has been measured by using a thermocouple. The temperature is being measured by using a thermocouple. The signal has been measured, converted, and then this signal conditioning has to be done. This is the second stage, signal conditioning has to be done, and then we are getting in the form of voltage resistance, voltage responses. This temperature has been measured in terms of voltage responses. Right. So we can take one more example of the pressure sensors. Here what we are using? Here we are using the piezoelectric content, a piezoelectric sensor which converts this pressure into the electrical responses. We want to measure the pressure, how much it is. Right? So this has been converted here in terms of through transducer element, as a electrical responses. Right? The sensors with transducers only it comes. Thus we can name the sensors are transducers. So again one more thing I am giving an example. A flow, a velocity we have to measure here. Right? And here again we are using ultrasonic flow meter. This ultrasonic flow meter is sensed and measured, and the signals are passed here. Signal sensors, responses, signal responses. And what happens is transducer element here, the transducer element converts into the electrical responses. So we are going to see in the upcoming sessions about various types of sensors. Displacement sensors, position sensors, proximity sensors, velocity sensors, flow level sensors, water level. So those light sensors, various sensors we have to see. I am dividing these types of sensors in two forms. One I am dividing these sensors in form of internal sensors and external sensors. You see, the internal sensors are used, is like our skin. When I am considering as it may be a skin as internal sensors and eyes, ears as external sensors. The parts which what happened inside it measures. Typically we can take here, which is used to operate the drive units. It's used to operate the drive units. What are they? Maybe the positions, maybe the velocity, maybe the acceleration, maybe the force, These types of sensors are belong to internal sensors. What happening inside the machine setups, it counts. But what happening in the environment, are known as external sensors. Right, you see, the temperature we have to measure from there, visuals, proximity sensors, acoustic sensor. This belongs to the external sensors. So I am divided as a human being, as here my eyes are belong to the external sensors, right, and my skin belong to the external and skin belong to the internal sensors, right. So a few examples are given. I am also dividing the same sensors in the second form with respect to contact sensors and as a non-contact sensors, right. So you see, there in the sensors we have a physical contact. It touches, like a mobile phone, it touches. Those comes under as contact sensors. These contact sensors are physical contact between the sensor and the object. Sensors and the object. So I am dividing again these two. For our understanding, I am dividing again these two as a touch sensors, tactile, binary sensors, right, which indicates presence of or absence of an object. It indicates the presence or absence. When you touch it, you understand whether it is okay or not okay. When you touch the touch sensor, the mobile operated. So there we are using the contact type sensors. So there, that's right. The force sensor is there. Here we are not only we are touching, we are giving pressure also. We are giving pressure additionally. Like we can use, we have already learned this strain gauges, which is used to measure the displacement. There, the contact between the workpiece and the sensor happens. It not only touching, it also the force is applied to break the specimen, and we are going to measure the stress applied. The strain displacement happen, how far it is, whether the tensile or the compression force applied, whatever it is, we are determining through the sensors strain gauges. So we can not only the contact is made, but also force is measured here. Right? Like example, there what I told you, the strain gauges is given here. Right? So this is one type of contact sensors. The other end we have a non-contact type. See what are they? Again, the proximities, visual, acoustic. This all we have seen in the environmental sensors in the previous slide. See, this visual, acoustic are available here. See, the visuals are available in the external sensors. The same, I am categorizing in two forms. Here it is in contact, non-contact method. Right? So we all together we want to see more than 8 to 10 sensors in the upcoming sessions. See, we want to know before going to characterize, before going to know about the types of sensors, we want to know about the characteristics of sensors. Few things, what it can able to do, the sensors, what the ability it needed. First one is the range. We know this even though we should. The difference between the maximum and the minimum. The difference between the maximum and the minimum of the input that can be measured. The difference between the maximum limit and the minimum limit. How much range it can be. It may be a temperature. We can take example. A furnace. We can take a furnace example. Here, a furnace can able to take a range of temperature maybe up to 800 degrees centigrade maximum. What is the minimum? It can be heated from low level of the room temperature to 800 degrees centigrade maximum. This is the range. This is the range of those sensors can be measured. Above this, what happens? The sensors loses its characters. Right? So that is like the range. And one the response, how fast it is able to do, how fast should be capable of responding, to the change in minimum time. Very fast response to be there. Now I'm taking one example of a box, a system, and I'm giving you one input temperature. We need a temperature of 22, and the output signal we are getting a temperature of 24. Immediately we should change by using a feedback system, by using a feedback signal. But what happens if the response is too lagging with respect to time? We keep on to understand the give, and we keep on giving the input we need, but the response is not, it's wrong. Right? So we need a quick response in a less time. That is about the response. Next, the accuracy. Whatever we are measuring, there should be no deviation from the exact quantity. Sometimes the transmission element may be wrong. Sometimes the sensing element may be wrong. Right? Let us take the same example of a furnace. You see, when the temperature is heated, the condition, the maximum is 800, but we are only heated up to 750. Only when we are heated up to 750 degrees centigrade, but when the sensing element or transducing element is not working properly or not showing the result accurately, it may show instead of 750, it may show 800. So what happens, you see? So what happens? The accuracy is spoiled, we understand wrongly. The temperature is only 750, but we understand it is 800 and we stop the setup. Because the maximum range is 800. We should not move above there. Therefore, we stop here. The next. So in case of sensitivity, what is it? Is equal to change in the output by the change in input. What we have given, it should be accurately, it should reach us there. Therefore, sensitivity should be also very importantly to be considered as a character. Then repeatability. I am taking more than 10 times of the same parameters. Then what happens? The deviation should not be changed. The deviation from reading to reading. When these are taken for number of times, under identical condition, the parameter is same and operation are same. Output should not change. The output should also be same. Right? Likewise, we should have a good repeatability. Then the resolution, the smallest change of precision it can detect. What is the minimum quantity? How the temperature here I have mentioned 32. What is the minimum quantity? The very, very lowest minimum quantity it can measure, that is 31 here. Up to our condition, the minimum temperature is 30. Likewise, minimum, when we mention the displacement, how much displacement you can measure, the resolution of 0.0001 mm we can measure. Likewise, they have displacement or weight measurements. 0.00 not what on gram measurement, that is called resolution. So here I want to show you a small video.
Sensors are a part of everyday life at home and work. There's probably not a day that goes by where you aren't impacted in some way by a sensor. Sensors are the figurative eyes and ears of a control system. In general, if you want to control it, you must sense it. Because the controls engineer is often called on to specify sensors and deal with sensing problems, sooner or later, we will all get more than enough familiarity with them. In this video, we are going to familiarize you with the sorts of sensors that we frequently use in industrial equipment. We intend this to be an introductory video for a new engineer just getting started. or for anyone looking for a general understanding of some general controls concepts. All right, let's go. The smart sensor plays a very important role in the smart factory of Industry 4.0, which is considered as the fourth revolution of the manufacturing industry. The first revolution brought us steam and water-powered mechanization. The second revolution introduced mass production using electricity. The third revolution established automated manufacturing processes using computers and robotics. And now, the fourth revolution has launched the Internet of Things, or IoT, and the smart factory. What makes a base sensor different than a smart sensor? A base sensor is a device that senses something. A sensor is a device that senses something. Today, we have sensors that can see, feel, hear, smell, and even taste. Without sensors, our home and work lives would be quite difficult. For example, as you drive to work, the traffic lights at an intersection are controlled by sensors embedded in the road. These sensors detect your arrival at the intersection. As you approach the grocery store, the door automatically opens because of a sensor. In your plant, the batch process temperature and pressure are displayed and controlled as a result of output from sensors. In the world of instrumentation and process control, we define a sensor as a device that detects changes in physical, electrical, or chemical properties and produces an electrical output in response to that change. What are the typical physical properties that sensors are detecting? Let's name a few: level, temperature, flow, pressure, speed, and position. From a process control perspective, we can classify sensors as either passive or active. A passive sensor requires an external source of power to operate, while an active sensor does not. A thermocouple is an active sensor, as it does not require any external power supply to operate. As a thermocouple is exposed to an increase in temperature, it will develop an increasing voltage across it. Another example of an active sensor is a piezoelectric sensor. A resistance temperature detector, or RTD, is a passive sensor. It is a device that's resistance will change with a change in temperature. To take advantage of this change in resistance, an external supply, or an excitation circuit, is required to produce a change in voltage. Another example of a passive sensor is a strain gauge. All right, now that we've talked about sensors and the physical properties that they can sense, let's discuss how they are used in the industry. Almost every sensor used in process control will be connected to a transmitter because the sensor's output needs to be conditioned or amplified. Here's an example. We've already talked about a thermocouple and the voltage output created when it is heated. Unfortunately, the voltage output of a thermocouple is minuscule. In our example, the thermocouple will produce a voltage output from 8 millivolts to 18 millivolts over a 450-degree Fahrenheit change in temperature. In process control, we condition that 8 millivolts to 18 millivolts thermocouple voltage and convert it to a 4 milliamps to 20 milliamps industry standard signal that represents our controlled temperature range. As a controls engineer, we often tend to see things from the electrical end of things. So in this exploration, we will look at two broad categories of sensors: digital sensors that return on-off signals and analog sensors that return a range of values. Our first stop is digital sensors. These are by far the most commonly used sensors in the industrial world. So, what is a digital or binary sensor? In theoretical terms, we're referring to something that returns one or more bits of information per sensor. Initially, they were simple: a contact that touched another contact when something got where it was supposed to stop. In those old machines, this often meant 110 volts exposed for the operator to touch, or passing through the machine frame. unsafe under any condition, and probably illegal in today's safety-conscious world. Later, these became a switch that flipped when something got to a position. These are referred to as limit switches and are still in use. We use these sorts of sensors for anything that we divide into two states: on and off, true and false, is and isn't. For example, in position, full, empty, power on, and running. Let's look at a few examples of these kinds of sensors. First, as mentioned before, mechanical switches of various kinds are still around. Limit switches are still used in ugly, dirty environments thanks to their armor-plated construction. One big reason they have become less popular over the years is that they're huge compared to many of the other sensors available. Proximity sensors, very often called proxies, are used for detecting close metal objects using magnetic fields. In many environments, these have replaced limit switches in position sensing applications. Optical sensors have a much longer range than proximity sensors, but they are susceptible to dirt and other environmental and mechanical issues because they use light for sensing. We often use them where we are not picky about exactly where the target is, but we need to know it is there, like boxes on a conveyor, where we don't care where on the conveyor it is, just that it's passing by. Capacitive proximity sensors are like a proximity sensor, but for detecting non-conductive materials. They are very sensitive to contamination, and historically have not been very dependable. Ultrasonic proximity detectors detect solid objects using high-frequency sound, but are very susceptible to environmental conditions and dirt. We don't use them often, but they can solve sensing problems nothing else can. An auxiliary contact is a part of a relay. These tell us when whatever is controlling the relay has turned it on or off. A push button senses the operator's action. For now, that's all we'll say about digital sensors. Most controls are still designed around on-off signals, so these are the bread and butter of a control engineer's life. At one time, cars had no fuel gauge, and you had to have a reserve tank, a gas can, so that when you ran out, you could get to a fuel station. Now, cars all have fuel gauges, and we will next look at the sensors that make that possible, along with many other measurements that automation requires. An analog sensor is one that converts a variable physical quantity into a signal that the control system can understand, a voltage or current. By physical quantity, we mean temperature, pressure, humidity, distance, and speed. Okay, so what if we had a sensor that did more than sense singular basic physical properties? What if we had a sensor that also performs data conversion, digital processing, and can communicate to external devices and the cloud? In very general terms, a smart sensor has a base sensor, a microprocessor, is communication capable, and has some form of onboard diagnostics. Smart sensors are capable of a variety of functions and options. Smart sensors can perform self-assessments and self-calibration. They can detect issues such as sensor contamination, switch failures, and open coils. Some smart sensors are capable of multi-sensing and can measure pressure, temperature, humidity, gas flow, and more. Smart sensors play a very important role in the new era of manufacturing intelligence. They will become more and more important as industry develops increasingly sophisticated and complex processes. We have just taken a whirlwind tour of the primary sensors used in almost every industrial control system. With these sensors, we sense everything from which buttons the operator pushes to the height of liquid in a tank to the pressure and temperature of steam in a boiler. These sensors and a few others, with their signals processed by hardware and software, control the industrial processes of the world.
Right. So the remaining sessions, the remaining topics we'll see you in the next class. Thank you.